Hello, everyone. Okay, so let's start with the second meeting. So let's see. We left off last time discussing about. I flew through the definition of representations, I think, very quickly. I just want to ask, did you guys internalize the definition of a group homomorphism?
So I actually wasn't there. So if you could just go over
Okay.
that quickly, that would be great.
Okay. Are you okay with the definition of a group?
Yeah, I think so. I think
Okay.
it's just kind of like any collection of objects.
Mhm. It's
Mm,
any collection of objects with certain axioms.
properties.
Yeah, so I posted the lecture notes for last meeting in the Discord. So if you wanna like you can read up on that at any time. Okay. So let me just define a group really quickly, just so that we have a recap. Recap. Oh, sorry. Recap. Definition. So we have a group is a set G with a binary operation. So binary here just means it takes in two things, gives you one. Um, all this dot that takes in two elements of your set gives you one, such that for all x, y, z, and g, there exists E. Okay, so I'll define this as there exists a unique E in G. You can show that identity elements are unique, so this definition doesn't really affect the class of groups that we have. There exists an element G such that x dot E equals E dot x equals x. Um, there exists an element x inverse. Again, there exists a unique element called x inverse in G, such that x dot x inverse equals x inverse dot x equals E. And then finally, x dot y dot z bracketed like this and bracketed like this are the same. Okay, groups are natural to study because they describe symmetries of your system. Um, Last time I gave the example of how a quantum state is invariant under multiplication by a complex number of norm one. We also saw how this correspondence, say this symmetry, gives rise to the conservation of probability um, for that specific system. So it's actually a um, theorem by Emmy Noether that says that any symmetry that a physical group has, any symmetry that your physical system has corresponds one to one with conservation laws. Um, so you've seen this a very quick example is Newtonian physics is like a lot of Newtonian physics is invariant under like spatial translations. And spatial translations therefore correspond to um, conservation of momentum. So okay, let me give you a concrete example. Say you have a ball that's dropping, right? Now, this system is not invariant under like translations in Z, right? Therefore, the momentum in the Z direction just cannot be conserved. However, this system is invariant if I move back and forth, the left to right. This tells me that um, the X momentum and the Y momentum are conserved. We will prove Noether's theorem in more generality when we talk about Lagrangian mechanics. Um, so yeah, are there any questions for this so far? Like, are there any questions for why we talk about groups? Okay. Now, since this is a mathematical physics discussion. We want to bring in math somehow. The main goal of math is studying objects and studying maps between the objects. That's the field of category theory for the most of it. You want to study objects by how they interact with other objects using maps. But we'll postpone that formulation for like a little bit. But okay, um, let's define the maps that we want to use for group theory. Like in linear algebra, we had linear maps that preserve the linear structure of our space. Similarly, in this case, we want maps that preserve the group structure. So a group homomorphism. Um, I'll write homomorphism usually. And then depending on context, I think you can figure out if it's a group homomorphism, ring homomorphism, vector space homomorphism, etc. So group homomorphism is a map phi from a group to another group. Um, Here I'm suppressing the operations. So the operations in G and H are suppressed. Um, just because it gets cumbersome to write down the operation on each set every single time. But it's sort of implicitly known. If for all G, H, and G, 5GH is the same as 5G times 5H. Okay, so these are group homomorphisms. Basically, you can do multiplication inside or outside, it doesn't matter. Okay. One more additional thing I want to say is that not every group is commutative, so the order of multiplication does matter. Groups in which, so let me just give you another side definition. So if x dot y equal y dot x for all xy, um, then G is called abelian. So abelian is named after some like mathematician. His name was like Abel. Um, I was watching a Richard Borchers lecture. If you don't know who that is, he's a Fields medalist. Not sure what he did exactly, but I know he won a Fields medal. He was talking about how Abel actually died in his like early 20s. I'm in my early 20s as well, and I have not done anything significant enough to have something named after me. Okay. Um, okay, so are there any questions about groups and maps relating groups? Okay, that's wonderful. Okay, so another just quick definition. A group isomorphism is a homomorphism. Again, group is implicit. Um, that is bijective. And the inverse is also a homomorphism. As an exercise, I'll let you prove that it's enough to assume that your homomorphism is bijective for this to hold. So you can remove the assumption that the inverse is also a homomorphism. Um, it's very quick, like just manipulations. I think a lot of group theory proofs sort of rely on this easy manipulation, at least for the beginning. Okay. Those are like the main definitions. We talked about like some classical groups last lecture. So if you want, um, you can check out the lectures, like the lecture notes from last week. Okay. Um, so in physics, we don't care about any of this. what we do care about is how groups act on physical space. Um, so we can define this thing called, okay, so this is now new stuff. I didn't define this last time. So definition. Actually, let's motivate this by an example. So say we have the group GLNR, GLNR. An object in this group is now a matrix. Is a matrix. Is an n by n matrix, if you will. Now, if I assume that I pick the standard basis, right? Assume E1 up to En and Rn is the standard basis, then I have a natural action, whatever an action means, of this matrix on my vector space. Okay? I now have a natural action of A on Rn. So what do I mean by this exactly? What I mean is I can take A, and I can multiply it by some vector V, right? In the usual matrix multiplication, right? Just take any vector, I can multiply it by my matrix, and I get another vector. And that's so in some sense, this matrix has now acted on this vector space as a linear transformation on my vector space, right? So A has done the role of a linear map on Rn. Now this idea is extremely central, right? This idea that we have some group and it acted on um, an object of some vector space is extremely central. And so we generalize this to the following. So definition, let G be a group. Oh my God, the Zoom meeting is ending in 10 minutes. So I'll make a new Zoom meeting. Um, okay, so let G be a group and let A be any set. Okay, doesn't have to be any particular set. Now what we're going to do is we say G acts on A from the left if um I don't want to define. Okay, so we have G times A. Firstly, is an element of A. So we're defining an operation on A. Okay, let me actually write this nicer. If there is a map G cross A into A, okay, taking G and A into this element that I'll call G dot A. This dot shouldn't be confused by the dot that I have for the group operation. And that's why for the group operation, I don't write the dot. But for the group action, I will specifically write the dot most of the time. If I forget, please forgive me. Um, and point it out if I forget it. Okay, another one. So the first property is that E dot A is equal to A. So it shouldn't change anything. And the second property is that G acting on H, acting on A, is the same thing as GH acting on A. Okay, that's it. This is all we require. Does this make sense?
Yeah, is there anything from the right?
Yes, yes, there is an action from the right. So let's define that as well. We say G acts on A from the right if there's a map G cross so A cross G into A, mapping like this, such that A dot E is A and A dot H dot G is A dot HG. Okay. So, so one quick remark. Um, say we say the G acts on A from the left. Okay. So we have GA maps to G dot A. We can now actually make this into a right action. Okay. We can make this into a right action by defining A comma G as G inverse dot A. So I highly recommend you check this because this will help help you understand like right actions and left actions are slightly different, but you can get a right action from a left action and you can get a left action from a right action. So the bulk of the theory that we're going to work with is going to be with the left action. There are certain cases actually where we'll have a space that acts from the left, and then there'll be an associated space that inherits a left action. Okay. So it's good to keep in mind that right actions and left actions exist, but we'll mostly care about right actions. And the reason we mostly care about right actions, sorry, left actions. The reason we mostly care about left actions is because matrix multiplication is a left action, right? We can see that immediately, I think. Or would you like me to explain it? Like, does it make intuitive sense as to why matrix multiplication is a left action?
Yeah. That
Okay.
makes sense. Now I have a small question as to
Hmm.
what about both right and left? Is that something that exists?
Yes. Yeah, I mean, there are right and left actions, but we have no use for them for the most part. Um, funnily enough, the main example that I'll have today is a left and right action. Um, actually, hold on. No, I don't think you can have a left and right action. The reason for that is, um, if you write right actions the way we wrote left actions, they actually swap the order of multiplication in G. So what I mean by that is if I wrote this as E dot A instead of A dot E, this would just be A, and then G dot um, H dot A would have to be defined HG dot A. So you see, I had to flip the order of G and H here when I came here. So I don't think left and right actions quite make sense because I don't know how you would do that. Um, but maybe it does exist. Maybe I'll look into that. I'll get back to you on that. Um, okay. A very important example of a very important example of an action we will use again and again, is called conjugation. So let G be any group. We then have a map, G cross G into G, that takes in an element G and another element H and gives you G H G inverse. So if you see, this looks extremely similar to the change of basis of matrices.
I thought this looks like the diagonalization or whatever, the
Yeah,
eigendiagonalization,
yeah, exactly,
the
exactly.
PDP inverse or whatever.
Yeah, exactly. So we're sort of trying to generalize. We're trying to generalize, like see, and we're trying to see if if that is actually a universal property of groups. Like, is that an important concept in groups itself, or is this something that is a byproduct of the way the group acts on the vector space? And as it turns out, that this map is actually extremely important. Um, and we'll see that conjugation is very inherent to the structure of groups. So in the readings that I assigned for group theory, you will learn about this object called a normal subgroup. And normal subgroups are basically subgroups that are invariant under conjugation. And these play like a crucial role. These play a crucial role in algebra all throughout. Okay, wait. So the meeting is ending in 1 minute. I'll just make a new meeting, and then we'll pick up from here. Yeah. Just give me 1 second. Way too long. Okay. Okay. So yeah, it turns out conjugation is actually a very important group action. Let's actually make sure that it actually is a group action. So note that we added this way. So E dot G is the same thing as E G E inverse, but this just equals G. That's fine. Now let's do H this. This is so now G acts on H. Sorry, this should be. Let's do Z. Okay. And then this is HG Z G inverse H inverse. And now one thing we need to note as a side note here, HG inverse is equal to G inverse H inverse. Now we can check this. Would you guys like me to like go like check this, or can I leave this as an exercise?
Just check it once.
Okay. So I'll check it for this case, and then you can work through inductively trying to figure out if I have a bunch of elements and I took their inverse, um, how like how the flipping of order works exactly. Okay, so to check this, we need to check that HG inverse times G times H is equal to the identity. Right, that's what the definition um, what the definition says. Okay, but now, but we can do this just by what we can do now is we can take HG inverse and multiply. Actually, okay, so there's actually two things we need to do. One is we need to check that inverses are unique. So need to check inverses are unique. So let's do this really quick. So let's suppose that Z and W are inverses of G. So what this means is that GZ equals GW equals the identity. Okay. But now I know that Z equals E times EG. Sorry, this Z equals E times Z. But then E times Z is the same thing as G WG of Z, right? Because, okay, I didn't write all this, but we have this. Okay, but then let's use the associativity of groups. So we get W times GZ, but GZ by definition is the identity. So this is WE and this is W. So we get that Z must equal W. Okay, so inverses are unique. Now we just show that HG is an inverse of this element. And then by uniqueness and by I guess another thing you have to check is that the inverse of the inverse is the original element. So need to check x inverse is equal to x. I'll leave this as an exercise. It should follow immediately from like uniqueness of inverse. Okay, with all this out of the way, let's look at G inverse H inverse, and let's multiply this by HG. And then using associativity, we get G inverse HG. But then H inverse H by definition is the identity. So G inverse identity G. And then this is this identity. So then by uniqueness of the inverse, we see that HG inverse is nothing but G inverse H inverse. So taking the inverse swaps the order of multiplication. Okay, coming back, then now we see that this is HG Z HG inverse, which is the same thing as HG acting on Z. Since our action didn't swap the order of multiplication, we can see that this is a left action. Because if we look at the definition again, this one, we see that so the order is GHA, and then in our check, we have HGZ. So it must be left action. Okay, so conjugation is a left action. Okay, are we happy with this example? Okay. So now let's get to the next definition, and that is of a representation. A representation of a group G on a vector space V, and here V can be over R or C or any field of your choosing. In fact, I don't really care. But the ones we'll mainly focus on are R and C. A representation of a group G on a vector space V is a group homomorphism I from G into the general linear group of V. So the general linear group is just the group of invertible linear transformations. Okay. So if we see the matrix group the matrix group GLNR has a representation on Rn where we just send a matrix A to the action linear transformation. Okay. So now representations are extremely important when we're studying physics. And it's mainly important when we're studying quantum mechanics. The reason it's important when we're studying quantum mechanics is because one, Noether says that groups are very important because symmetries are very important. The other reason is state space is a Hilbert space, or at least the surrounding space of a state space is Hilbert. So we have some sort of linear structure, and now we want to see how I can have group elements acting on my Hilbert space to mainly get conserved quantities, but there's also like other implications that we can get from thinking about it this way. Okay, have you guys seen the pauli matrices?
No.
Okay. Okay. Let's take a detour into physics now. Detour. So we have the Stern-Gerlach experiments, right? The Stern-Gerlach experiments. So we have our array of silver atoms. We have a inhomogeneous magnetic field here. And then the silver atoms come in and then they get deflected like that. And we call this like the upspin and we call this the downspin. You guys have seen this, right?
Yes.
Okay. So this isn't a particular basis, right? Like the reflection of the silver atoms going up and down, they depend on the axis at which they're going. The usual Stern-Gerlach experiment keeps this in the z-axis. So this is going up and down in the z direction. But then you also have you can turn this to the side and then it goes left or right. And then you can turn it the other way and then it goes forward or back. So then you have like different bases um, to describe like the same particle behavior. Okay, so we know that this is caused by the intrinsic angular momentum of the last electron in the silver atom. I think it's the 47th electron in the silver atom. Um, and then we know that the whether it goes up and down is probabilistic with probabilities. So I can describe the state of my silver atom as a vector where alpha and beta are complex numbers, where alpha, beta are complex, such that the norm of alpha squared plus the norm of beta squared is 1. Okay. Okay. So now say I have my measuring operator called um, just to be extremely pretentious, I'll call it sigma z. This is what I don't know why it's called sigma z, if I'm being completely honest. But this is one of the Pauli matrices, and the idea is that it acts on the upstate by giving you the upstate, and then it acts on the downstate by giving you negative of the downstate. Okay. So now the matrix representation of sigma z in this basis is it's a diagonal matrix, so that's very good. And the diagonals are just the eigenvalues, so it's 1 and -1, like that. Okay.
What is the negative of the downspin?
I mean, you don't want to really think of like the negative of the downspin doesn't really mean much, right? In terms of like what state it gives you. The only thing you really care about is that you care about the constant in front. So you can think of the upness of a particle as being like the number one, and then the downness of the particle being -1. That's all it's saying. It's just a way to differentiate between up and down.
So is there one for like the reverse if you have negative upspin and positive downspin?
So yeah, I could have defined the action of sigma z on up as being negative up, but I mean that's just like if I reflected my apparatus,
Oh,
right?
yeah. Okay.
So
So
is
it
it
doesn't
like
matter which direction
yeah,
they go?
yeah, because there's no intrinsic direction. That's the main idea. Like in an abstract Hilbert space. So in this case, these states form a two-dimensional complex vector space, and there's no like preferred direction for you to go in, right? There's no orientation or anything of that nature on this space. So by convention, you choose the eigenvalue of up as being one, like the measurement of up being one, and the measurement of down being -1. It has no physical implication. Um, the only thing that has physical implication is if it's up or down, like if the vector itself is up or down. Okay. And now we know that the probability of this abstract vector, probability of abstract of this vector of like up is given by, um, I don't know if you've seen this, but it's given by, let me call this like psi. So it's given by this squared. Have you seen this?
Briefly, very briefly. But
Okay, yeah. So the probability of up is this, and the probability of down is this. And this is why we need alpha squared plus beta squared to equal 1, because this, if you compute this out, you get the norm of alpha squared. And if you compute this out, you get the norm of beta squared. So okay, so this is one of the Pauli matrices. One of the Pauli matrices. Um, the important thing is this is in the Z basis, in the sense that this is in the basis in which up and down are determined by the Z-axis. And now there are derivations. I can link some derivations, but the spin matrices for the x direction in the z basis are given by this matrix, and in the y direction it's given by uh, this matrix.
oh, what? Why all of a sudden is now I the imaginary plane?
If I remember correctly, I think it's to differentiate between x and y in some way, but I'm not too sure about that. That's why I'm saying like I'll link like an actual resource where you could check this out.
Oh, okay, that's perfect. Thank you.
I think the idea though is you want to chain these Stern-Gerlach experiments together. So you want to take a beam of silver atoms, they go through the Z um, magnetic field, and then you take whatever is up, for example, and push it through the Y Stern-Gerlach one, and then you like you try to interpolate how the Z like how the Z basis relates to the Y basis, And then it's like a change of basis that gets you this formula.
Okay, okay.
Yeah, so you're just trying to figure out like if in it like if I how does like mm, yeah, so what you look at the probability of okay, so say I get all the up states and I put them into like a Y start, let me call this an SG machine. And then I get like some of them go up, some of them go down. Right?
Hmm.
So some of them go up in the Y direction, some of them go down in the Y direction. I look at the probabilities here, and that tells me how to write my Z in terms of like if the probability of it going up is alpha, is like delta, and the probability of it going down is epsilon. So I just have to choose numbers alpha and beta, alpha and beta that have like norm squared equal to delta and norm beta squared equal to epsilon. So that's the idea. Like you work through this, you do the math, and then to differentiate between x and y, you choose one and I.
Okay, so just so I have, can you just scroll up 2 seconds to
Okay.
the picture? So just say if I have it correctly,
Mhm,
um, you can pick the direction that we pick for our basis is arbitrary, so
mhm.
long as we can find two complex numbers that give us the equations in the other bases.
I mean, it turns out that you like if you have a basis, you can move to any other basis.
Yeah, just using different
Yeah,
vectors.
and one very important thing to note is that like this ties back to the discussion last week where we multiplied our like state vectors by um, a complex number of norm one, and it did not change anything um, in terms of the information we have about this state. So that's why we have a freedom of complex number up to norm one. So like you can choose just any norm one vector, and it like doesn't really matter. But just by convention, we choose like one and I because those are like the nicest norm one vectors. So no, norm one complex numbers. One I,
Okay.
negative one, and negative I. But in reality, you could have chosen like any other numbers you wanted. Like there's nothing specific about one and I, as far as I know. Uh, I might be wrong, but as far as I know, there's nothing special about these numbers. Because like the only thing we care about in terms of like a state is that the probability it gets us a certain measurement. Um, and the probability doesn't care about norm one complex numbers. This is called U1 gauge, like gauge freedom. U1 here is the group gauge. So the word gauge means a lot of things in physics, but yeah, I think in this case it means like potential. Usually it's like a choice, like when you're fixing a choice or you're fixing a convention, you say you're choosing a gauge. Um, if you've done any E&M, you might have heard of like the Lorentz gauge or the Cauchy gauge. If you haven't, I
Yeah,
mean,
we're doing
it's
that. We're doing
oh,
that
okay,
like now, like at 250,
okay,
physics 250.
okay. Yeah, so gauge just means you're like picking a convention, sort of. And U1 gauge freedom means that your convention is equivalent up to like a U1 transformation. Okay. So these are the Pauli matrices. At least that's the convention of Pauli matrices we'll use. There's usually a fourth vector that I'll add on called sigma zero, and this is just the identity. This is just the identity matrix. Okay. Are we okay with this so far?
Yes, sir.
Okay.
Actually, this is
So
kind of making more sense now that there is a quantum example.
okay, that's good. That's good. Yeah, I mean, so the idea is that like there's actually a very funny story where Heisenberg um, discovered matrix mechanics on his own um, when he was like alone in some island because he was sick, so he was like quarantining. Um, so he went off to some island and he discovered matrix mechanics, and then he came back um, to his advisor. I think his advisor was I think it was Max Born. So he went back to his advisor and he said that he doesn't really understand why there's like I'm multiplying these two objects, but they're not commuting with each other. And he showed him the formula, and then it turned out that um, it was just matrix multiplication. And Heisenberg had never heard of matrix multiplication up until that point. So matrices and actions of matrices on quantum systems are very, very fundamental. So if you were to discover quantum mechanics on your own, you would have discovered the action of groups on states like independently, as Heisenberg did. Um, so that's why I think it's good. Like it's important to have like the math background so that it can help you with the physics. Um, and a lot of the times there are times where like the physics really motivates the math. So I mean it makes sense as to why it makes more sense because like these are very intrinsic properties of quantum systems. Okay, now I'm gonna do something that's very unintuitive at first, but I hope you'll realize the true power of it in just a bit. One thing I want you to notice now is that these three matrices are linearly independent over the real numbers, right? Sigma x, sigma y, sigma z are linearly independent over R. But we have three vectors that are linearly independent over R, and then from a um, from a basic theorem in linear algebra, we know that this can be thought of as R3. Okay. Um, the isomorphism we'll give is we'll take a vector x, y, z, and we'll map it to x sigma x plus y sigma y plus z sigma z. Okay, is an isomorphism. Are we okay with this so far? So, what is the purpose of this? You might ask. Well, like, why would you ever do this? Um, and it turns out that the answer is a little um, lengthy. So let's take some time to do this. So if you remember SU2, if you remember SU2 is the so it's the group of matrices. It's a group of complex matrices, like two by two complex matrices. Oh my God, the meeting's ending in 10 again. Such that the determinant of A is 1 and A dagger is A inverse. Okay, so this is SU2. I'll leave it for you just for the sake of time to check that um, every matrix has the form alpha, beta, negative beta bar, alpha bar, where alpha, beta are complex, and the norm of alpha squared plus the norm of beta squared is 1. I'll leave this as an exercise for you to check. Okay. What this actually tells you now is, okay, let's go back here. Now we can see that these four matrices are all linearly independent over the real numbers. Okay. And these form another vector space.
Wait, sorry, could you just
And
repeat that quickly? Sorry.
oh yeah, so sigma 0, sigma x, sigma y, sigma z are linearly independent over the real numbers.
Yeah.
So they form a four-dimensional vector space over the reals.
Hmm.
And since matrix multiplication, like matrices can multiply together, it forms something called an algebra. An algebra is nothing but a vector space with a multiplication on it. Think of matrix multiplication if you want to think of an algebra. Um, okay, and one thing I'll let you check actually is that this is exactly the same as the quaternions. And when I say exactly the same, I mean the multiplication of these matrices behaves similarly to the multiplication in the quaternions. Um, so what I mean by that is check that. So one thing you need to check is that sigma I squared is -1 for I equal x, y, z. And if and you have that sigma I, sigma j plus sigma j, sigma I equals I times sigma k, where I, j, k are a cyclic permutation of 1, 2, 3. You can look up on Wikipedia that this is how the quaternions behave. Okay. So now this tells me that SU2 can be thought of as a subset of R4, right? With all its term having unit norm. So now you might be tempted to say that SU2 is a sphere sitting in four-dimensional space. And as it turns out, it is. SU2 is a three-sphere. We'll talk about this when it comes like when we talk about Lie groups. I won't show this right now, but SU2 is a three-sphere. So you can think of SU2 in now three different ways. One as matrices, one as linear maps, and one as like the unit sphere in the quaternions. I'm mentioning this so that you have like a bunch of ways to like think about the same group. And the important thing is like all these ways of representing the same matrix are equivalent for all intents and purposes that we have. Is this fine so far? Or am I going too quickly?
I don't even know if you could slow down at this point. Like we're kind of just going. So just keep going, man.
Okay. I mean, the notes will be like posted on the Discord, so if you have any questions, you can just like ping me and I'll respond. Okay. So the main takeaway we have now actually is that SU2 acts on R3. So if you remember, R3, you can think of R3 as a subset of R4, right? You can just set one of the coordinates to 0, and you now have a plane. And now you actually get a group action of SU2 on R3 by conjugation. Okay.
Is there like a derivation for that we could look at?
Yeah, I mean that was actually what my main plan was to look at this derivation, but we're running out of time. So what I'll do is I'll type up like an exercise that details like every single step,
Hmm.
and then I'll post it as an exercise on the Discord. It's not very lengthy from what I've done. It's like the parts that we have the knowledge to do. It's a page and a half.
That's
Um,
not what I'm worried about. I'm worried about figuring out what's going on.
oh yeah, no, so I can talk about that. So okay, we're thinking of SU2 as a 2 by 2 matrix of complex numbers, right?
Yeah,
And we're
and
thinking of
somehow
R.
that's in R4.
Yeah, so the way we send that to R4 is just like take this thing as a basis of R4,
Yeah.
like these four vectors as a basis of R4.
Hmm.
And now since these form a basis, we we get you can check that every element in SU2 using this, you can check that every element in SU2 has the form um, every element in here has the form A plus B, A sigma 0 plus B sigma 1 plus B sigma X, Y, B 3 sigma Z with with A squared plus B1 squared plus B2 squared plus B3 squared equals 1.
And why is it B?
Oh, I just chose some random like variable name. It's not really important.
But you chose B 3 times. There's three different variations on B. So
Oh yeah,
why?
no, that happened because I panicked. So I just wrote down B twice and I
Oh,
was too
okay. So
lazy
it's
to
like
erase it.
ABC. So like ABCD is fine as well.
Yeah, there's nothing significant about the names. Um, yeah, so now since this is just a matrix and we thought of a vector in R3 as a matrix, we can take our matrix like as we saw above, it can be written as alpha, beta, negative beta bar, alpha bar. Is it alpha bar? Let me just make sure. Doesn't really matter. Um, but yeah, since SU2 is a matrix and vectors in R3 are also matrices, you can do something like this, where T equals T1 sigma 1, T2 sigma X plus T3 sigma Z. And A is a matrix in SU2. So I'll post an exercise that like details this construction in proper detail.
Hmm.